Welcome to the Explainer. Look, if you spend your days building machine learning models, you already know the friction. You're trying to implement explainable AI, specifically concept bottleneck models, but you hit a wall. You end up bouncing between completely different machine learning frameworks, wrestling with incompatible code bases, and constantly translating data types just to make things talk to each other. It is exhausting, right? Well, today we're going to look at a pretty brilliant solution to this exact problem, a package called HumAIne CBM. We're going to explore how it completely removes the friction of fragmented ML frameworks. Here is our roadmap for today. 1. The fragmented XAI landscape. 2. Introducing HumAIne CBM. 3. The unified interface. 4. Smoke tests and installation. And finally, 5. Limitations and core rules. Okay, let's dive right into this. Section 1. The fragmented XAI landscape. So picture this. If you're working with image data, you are likely relying on PyTorch for label-free concept bottleneck models, or LFCBMs. But then, say you suddenly need to work with tabular data. Now you're forced over to TensorFlow to use tab CBMs. You basically have two completely siloed approaches. You're juggling totally disparate code bases, managing different dependencies, and constantly context switching between PyTorch tensors and TensorFlow tensors. It's a headache, it slows down research, and it definitely slows down deployment. Which brings us to our solution. Section 2. Introducing HumAIne CBM. Enter HumAIne CBM. This package provides backend-agnostic concept bottleneck models. The real genius here is that it unifies both the PyTorch image models and the TensorFlow tabular models under one single umbrella using a NumPy first API. Those phrases right there, backend-agnostic and NumPy first, are the absolute key. It means the library abstracts away all those messy framework details so you just don't have to deal with them anymore. So, the crucial point, really the technical and emotional core of the entire library, comes down to this exact idea. Users pass NumPy arrays and concept dictionaries, never raw framework tensors. No more fighting with tensor dimensions and framework-specific formatting just to pass data into your explainable model. You just use the universal language of Python data science, NumPy, and the library handles all the ugly framework translations under the hood. Moving right along. Section 3. The unified interface. This library is built to be incredibly modular and developer-friendly. First off, you get a single, friendly interface regardless of whether you're processing an image or a giant spreadsheet. Second, it's efficient because of optional backends. You can choose to install just the image dependencies, just the tabular ones, or, all of them if you need both. It also features a built-in concept bank loader, which is super handy for loading shared concept sets like CFAR, Cube, or ImageNet. Finally, when it comes to the actual explainable part, the interventions, you can simply intervene by concept name or by index, with all your explanations cleanly returned as NumPy arrays. Let's get practical. Section 4. Smoke tests and installation. All right, heads up on a really critical installation detail straight from the docs, just so you don't hit unexpected errors during setup. If you're installing the image backend or the all backend, the package will automatically pull OpenAI's clip directly from GitHub. Because of this, you absolutely must have Git installed and available in your system environment. It's a tiny detail, but knowing it up front is going to save you a ton of troubleshooting time. Once you're installed, the package comes with a couple of really useful smoke tests to verify everything is working smoothly. The first is smoke_label_free.py. This script trains a sparse head on synthetic concept scores. And what's great is it doesn't even require that clip download to run, so it's a super fast way to check your environment. The second is smoke_tabular.py. This one exercises the TensorFlow backend using synthetic data and concepts. But what's really cool here is that it also includes examples of save and load functions plus evaluation helpers, giving you an awesome template for your own tabular projects. Both scripts successfully exercise the core workflow loop. And what exactly is that core workflow loop? Well, it's these 3 rapid steps: predict, intervene, and explain. This is literally the heartbeat of using a concept bottleneck model. You make a prediction, you intervene on specific concepts to see how they impact the model, and boom, you generate an explanation. Both of the smoke tests we just talked about let you execute this exact 3-step sequence effortlessly. Let's move to our final part and see how this all builds together. Section 5, limitations and core rules. Okay, let's walk through a few specific constraints. And honestly, I want to frame these not as flaws, but as important operational rules. First, if you use conceptbank.load with a name like cifar10_filtered, it's only going to resolve if the corresponding files exist in sibling directories named label-free-cbm or tab-cbm. Got it? Second, on the image side, LFCBM assumes your inputs are already numeric image tensors. It does not automatically apply clip or torsion vision preprocessing for you. Third, the tab-cbm backend is a simplified Keras version. It relies on a single concept layer and a decoder, meaning it doesn't quite have every single regularizer mentioned in the original research paper. And lastly, just to ensure API consistency across both image and tabular formats, the LFCBM intervene method explicitly requires an intervention_dict parameter. Which brings us to the golden rule of HumAIne CBM. I really want to reiterate this core philosophy one last time, because it should be your main takeaway today. All public methods return NumPy arrays, framework tensors remain strictly internal. If you remember literally nothing else, remember this. It is the absolute defining feature that liberates you from framework lock-in. So, I'll leave you with this question to chew on. How could a backend agnostic, NumPy-first API accelerate your own explainable AI workflows? Just think about the time you'd save, the bugs you'd avoid, and the seamless transition between image and tabular data. This might just be the exact unified framework you need to push your models forward. Thanks so much for joining me on this explainer, and happy coding!